This is a recap of what we learned about in titrations. We had to bring our patience pants for that one because really we had to learn how to wait for that pink color to come along. But the first thing we talked about is acids. Like, what are acids? If I look at these three acids here, they're all acids. We learned from last week that acids turn litmus paper red. Red litmus paper will turn red or stay red, and blue litmus paper will turn red. So red is the color of acids. When I take a look at all of these, there's something I see in common on all the formulas. There's an H out front for all of them. Now, it could be more than one H, but these were the three acids that we looked at last week, and they all had one H out in front. Acids always have a hydrogen first, and what they have is an H plus, a hydrogen or ion or a proton. I kind of want to talk about that a little bit in a moment. So taking a look at these ones here, I see this has an H out front. I can see my H out front. This is an acid. And its acid goes, if you look at it on the other side, it looks like this. It has lost its H, so it loses an H plus. I know it loses an H plus because here it's neutral, and then on this other side it's a 1 minus. The only way it would become minus is if you lose a positive thing. So it lost an H, and not just an H, but an H plus. If we look at the other side, look at water. Water has now H3. That means it gained an H. And not just an H, it went from no charge to a plus charge. It gained an H plus. So here's an acid-base reaction where HCl is the acid, it lost an H, and H2O is the base. It gained an H. To recap that here, acids are H plus donors, and bases are H plus acceptors. Now I want to talk real briefly about this proton kind of word. So let's take a look at this proton, because you could say H plus is a proton. And that's kind of funny how you would think about that. So let's think about hydrogen, the atom itself. There is one proton inside the hydrogen atom. And I know that because hydrogen is number 1 on the periodic table. 1 on the periodic table means he has one proton. And that also means he has one electron hanging around him. Now if it says it's H plus, that means it has more positive things than negative things, which means I need to erase my one negative thing. Taking a look at what I have now, do you see how it's just a proton? If you have something that's an H plus, what you really have is just a proton. That's really what it is. It's taking a proton away. So taking a look at HCl, here's HCl right here in its formula form. This electron over here that goes with H normally, he actually hangs out by chlorine over here. You can see him right here. Chlorine has gained him, which means the only thing that's left behind in this red H is just a single proton. And that single proton happens to hook up right here. And there we are. It's hooked onto there. So acids are H plus donors, or they give up an H plus, and bases take on an H plus, or a proton. So let's take a look at this example. I've got NH3. I want to look for him on the other side. I'm trying to decide, is he an acid or is he a base? Well, I can see that NH3 has 3 H's, and now it's gained an H. This has gained an H plus. And if you gain an H plus, as we know up here, gaining an H plus is a base. NH3 is a base. Checking out my H2O on the other side. H2O is now OH. That means it lost an H. And not just an H, it went from no charge to a minus charge. That means it lost an H plus. H2O here is a base. Sorry, is an acid. Terrible. Okay, there we go. Acid because it lost an H plus. Why don't you pause the video right here? I'm going to ask you to find the acid and base in each equation. You're going to have one acid and one base. And then I'm going to show you the answers here. Give it a pause so you can check your answers. The acids are red and the bases are blue. One thing to notice about these examples, I want to go back, is if you look right here, I want to look at water. I'll use blue. If we look at water, water is an acid in this example. If we go up to my first example, water is a base right here. Water can be an acid or a base, and there's a special term for that. If you can be an acid or a base, like water is, then it's called amphiprotic or amphiteric. Amphiprotic is what your textbook uses. It can act as an acid or a base. So that means it could lose an H, it could lose an H, these things could lose an H, or it can gain an H. Since it's a minus, anything here would love to gain an H plus. A minus thing would love to be connected to an H plus thing. So these can act as an acid or a base. And the only way that you would need to know that is if you could look at it in an example. I wouldn't say like, is this amphiprotic? I would ask it through an example, if I or the textbook would ask it. All right, let's look at another kind of example. We're looking at bases now. When I look at these examples over here, these are very common bases. I can see there is a bunch of OHs every single time. A lot of bases will have these OH groups on them. The OH groups are indicative of a base. Your textbook goes into why and the examples of that. I've only got so many minutes on this video, so I'm not going to spend my time there because I don't think it's the most important part. What I think is most important is, can you identify acids and bases in a reaction? And then the second part is, if you react an acid with a base, can you predict what the products are? So that's going to be my part here. Here I can see there's H's up front. These are the acids, my first one. I can see there's OHs on the back side. These are my bases. I'm going to react an acid and a base together and try to find what the reaction would be. What would it come out on the other side? The first thing I need to do is determine what kind of ions I have. Acids and bases always dissolve in water, and they will form ions or charged particles. That's why acids and bases conduct. They form charged particles that are free to move. If I look at my H right here, and I look for H on the periodic table, you'll see he's in that very first column. Look at the periodic table for hydrogen, he's in the very first column. Everything in the first column has a 1+ charge. Which means if I happen to have 2 right here, that means this whole side is worth a 2+. Well, the other side has to balance that out, so that has to be worth a 2-. That way the whole compound is worth 0. It doesn't have any charge on the top. So this SO4 is worth a 2-. Right now I'm trying to figure out all the charges, then I can predict what they're going to be on the other side. So let's look at Na. He's in the first column of the periodic table, so he's called a 1+. We'll look at OH. He has to be a 1- then, because if this half of it is a 1+, and the other half has to balance it out to make a 1- and a total charge of 0. Okay, now I've got my charges. The parts that matter the most are these upper charges here, so I'm going to erase the rest. Now what I'm going to do is switch partners. When you've got acids and bases, the partners switch. In other words, this H is going to go over here to look at what's on this other side. If I was at H with a 1+, I'd want to be with a 1- thing. A plus wants to go with minus. So I make HOH. I'm going to take one H with me. Yes, I have 2, but I'm only going to take one at a time. There happens to be a bunch of H's floating around there. I'm just going to take one at a time. One H is an H+. With one OH, he's a 1-. And together they're happy, HOH. The other thing that happens here is I've got to make the other connection. So I've got my Na, you always take the plus thing first. He looks over here at this compound and says, I'm a 1+. If I'm positive, I want to be with the negative thing. Here's my negative thing. So my Na, write that first, is going to be with my SO4. Na is a 1+, SO4 is a 2-. That does not work out so well, so I'm going to put a little 2 here. That way I've got a 2+ with a 2-, and everything's happy. This goes back to when you're balancing compounds in one of the first few modules. All right, now I've got my 2 compounds. This is called an acid-base reaction. And the last thing I've got to do is put my numbers out front. In other words, balance the equation. I've got to put the numbers out in front here. So that's when I'm going to start counting. How many H's do I have? How many SO4s? And that sort of thing. So here, I'm going to look. I have 2 H's. This is that 1 H that came from there, so I need 2 H's. Now I've got 2 H's on both sides. SO4, I have 1 SO4, and I have 1 SO4 on this side. I have 1 Na, but on this side I have 2 Nas. So I'm going to have to put a 2 out in front of this one. Now I've got 2 Nas, and I happen to have 2 OHs. Oh no, I kind of messed up, but wait, there are 2 OHs here. So I officially have a balanced equation by having the 1, 2, 2, 1 coefficients. All right, let's try it again with the second one here. First thing I have to do is put the charges in. H is a 1+. It's that every time. In this case, this whole thing is a 1-. It's on the other side, so it has to balance. The K is in the first column, so he's a 1+. The OH has to be a 1- then. These are kind of nice because they have 1+ and 1- all the way around. Now I'm going to start connecting them. Take my plus thing, connect it to the minus thing on the other guy. HOH. Now take my other plus thing and connect it to the minus thing on the other side. KCOH. C2H3O2. This whole thing is worth a 1 minus, so I put that whole thing on there. K is a 1 plus. This whole thing is a 1 minus. It's good. I've got everything balanced here. 1 plus, 1 minus. And if you look at it, I've got one H on the left, one H on the right. One big thing on the left, one big thing on the right. One K on the left, one K on the right, one OH and one OH. This one is balanced without any more work. Take a pause. Let's try these practice ones doing the exact same steps. Then pause it here for your answers. All right, here are the answers. One thing you should notice that is in common every single time is you're always going to make water. That was true for these up here. Water and water. You can write water as HOH or H2O. I write it as HOH because it balances easier. And the other thing you make is an ionic compound. An ionic compound is a compound that has a metal and some other anion attached to it. So here, if I wanted to say it in a really general way, I would say an acid plus a base makes water plus a salt. Salt is a fancy word for ionic compound, at least fancy in the chemistry world. That's all it means. The last part of class we looked at is titration versus neutralization. So what we were just doing is neutralizing things. That means an acid is very acidic, base is very basic. If you put the two together in the perfect amount, you'll get a neutral solution. This right here on the product side is neutral. So that process of neutralizing to determine an unknown, whatever they have, it's called titration. So the science skill, the science lab you do is titration, and it's neutralizing things. So what I want to do, talk about the lab that we did in class, determine the molarity of the analyte HCl using 0.1 molar NaOH. This is where you need your patient's pants. What do you do for the solution to turn that pink, that light pink? Here's the procedure that we did. And what I want to do is kind of take you step by step on what happened in there and draw what the molecules are doing. I'm going to do that right up here. So the very beginning, we happen to have in our beaker, right here, we only had acid in there. Our acid would be the HCl. 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 So that's what it looked like at the very beginning. I'm going to draw it in a bigger beaker just to give myself some more space here. And what we happen to do is drop in NaOH over time. Na is a plus, OH is a minus. So here we go. I'm going to draw it up here. H plus Cl minus. H plus Cl minus. I'm just putting a couple in there because at the very beginning it was very acidic. We had a bunch of H pluses and a bunch of H pluses and Cl minuses. But then what we did was we would add a few drops of NaOH. So let's put in a drop of NaOH. Well, they'll kind of hang out there for a little bit, but then Na is going to be like, if I was Na, I'm a positive thing. I'm going to find somebody to be with, and I would be with a negative thing. And they would make NaCl. NaCl is now made. All right, well, that looks good. Now that he made that, OH is going to be like, well, I'm negative and H is positive. I'm going to be with that guy and make ourselves H2O. H and OH make H2O. So now if I look inside the beaker, I've got this going on. This doesn't look as acidic as before. I can see I only have 2 H pluses now instead of 3. It's not as acidic of a solution. I'm starting to neutralize it. Let's put in another Na plus 1, OH minus. Now that I put in another one of that, Na is going to look at Cl and say, yes, that looks good. Let's come together and make NaCl. And at the same time that's happening, OH says, yep, I see H plus. I'm going to go with that one. And suddenly he's going to make H2O. No longer is there going to be H pluses or OH minuses. There's going to be H2Os inside there. Now take a look at this solution. It looks a lot more neutral. I only have one H plus left. Let's put in another NaOH. As you guessed it, these guys will make H2O. And this Na will come over here to make NaCl. And now finally, if I see what I've made, I don't have any H pluses or OH minuses hanging out anymore. I've got, oh, wait a minute. This guy should be attached to somebody, H2O. I've got all neutral things. This is a neutral solution. This is where you would have your end point, your equivalence point. If you will pass the end point and you add more NaOH, then suddenly you'll have Na plus, OH minus, and that's a lot more basic. This now will be a pink solution. you have gone past the endpoint. It is now too basic.